So this is the group assignment presentation for ITS 61504 data mining, and I am Yap Jia Seng, student ID 0363912. And first, I will introduce the background of our project to you. So first, for the first problem statement, we are going to focus on classification. Is drug overdose pose a global public health challenge? So manual analysis is time-consuming and may overlook complex relationship. Machine learning enhance predictive accuracy and insight. So our objective is to develop a multi-label classification model using demographic data, including X, age, sex, race, and ethnicity. We apply data pre-processing techniques such as encoding categorical variables and standardizing numerical feature. The model was trained using multi-output random forest classifier and evaluated with accuracy, precision, recall, and F1 score. By predicting the drug involvement in the overdose case, this classification model enabled targeted intervention for high-risk groups. So this is the left side is the code of our data pre-processing. So first, we create a copy of the original dataset and we selected the relevant demographic and drug-related feature. We also encoded the categorical variable using label encoder. Then we split the data into independent variable and dependent variable. And we apply the trend test split with 80% of trend, 20% of test. We also standardize the numerical feature with standard scalar. So the second one is the clustering problems. The problem statement in the clustering problem is to identify the overdose hotspot. Identifying the geographic overdose hotspot is crucial for intervention, and the transitional report failed to track real-time trend. And clustering can help us to detect high-risk area for better resource allocation. And our objective is to use K-mean clustering to identify the overdose hotspots and extract the latitude and longitude from the datasets. To determine the optimal cluster using the elbow method and visualize and analyze the result for data-driven public health strategy. So this is the code used in the clustering programs. First, they also created a dataset copy for the clustering, and we define a function called extract coordinate to extract the latitude and longitude for the datasets. We apply function to the dead city geographic column, and we also remove the rows with missing the geographic data. And at the last, we selected early latitude and longitude as feature for clustering. For the third problems, we have anomaly detection. Problem statement, we have some overdose cases involve unusual patterns such as drug substance, unexpected demographic, and traditional methods struggle to identify these anomalies. Machine learning can enhance early detection of drug cases. Second, we have objective. Okay, objective, we have identified anomalies over those cases using machine learning, and we apply isolation forest, DBS, CN, and local outlier factor. We standardize feature to improve an anomaly detection performance. We also evaluate the model to enhance early warning system for drug-related threats. And this is the code of data pre-processing technique we use in the anomaly detection. We create the dataset copy, we select the features like age, sex, ethnicity, latitude, and longitude. We also do standardization using standard scalar and ensure numerical consistency for effective anomaly detection.
Okay, I will be the second presenter. My name is Deng Ziqi with student ID 0363937. I will present the following part. So 2.0 is implementation of data mining techniques. But first is classification. We apply multi-label classification using random forest wrapped in multi-output classifier. This is suitable for datasets where instances belong to multiple classes simultaneously. Why we use random forest? Because it has robust and accurate ensemble model. It builds multiple decision trees and aggregates their predictions. It performs well in imbalanced and high-dimensional data. So based on the code, we train on X trend and Y trend. It predicted outcomes on X test. It chosen for its efficiency in handling complex classification tasks. So the next is clustering. So in clustering, we apply k-means clustering to group data into meaningful clusters. We use the ALPO method to determine the optimal number of clusters. So for the ALPO method process, we calculated within cluster sum of squares, WCSS, for clusters range from 1 to 10. We plotted WCSS values to identify the ALPO point where additional clusters offer minimal improvements. Why we use k-means? Because it is simple, scalable, and efficient. It is effective in partitioning data into distinct, non-overlapping clusters. K-means can help uncover natural groupings in the data. It is a crucial step in unsupervised learning tasks like clustering. So based on the codes, it shows the optimal numbers of clusters. K, which is equal to 3, was selected. The model partitions the datasets into 3 clusters by minimizing the distance between data points and their respective cluster centroids. The resulting cluster labels are added as a new column in the dataset. So the third one is anomaly detection. So we will discuss the isolation forest for anomaly detection first. The goal for isolation forest is identify unusual overdose cases by using anomaly detection. Isolation forest algorithm with a 5% contamination rate will use. We split data into training and test sets. We detect outlier by isolating data points in fewer splits. When we use isolation forest, it is fast, scalable, and effective for high-dimensional datasets. It is ideal for detecting rare and abnormal patterns. So the outcome is it will highlight anomalous cases for deeper investigation, supporting targeted public health responses. The second one is DBS-EAN for anomaly detection. It is one to detect anomalies using density-based clustering. We use method DBS-CAN. So the key parameters in EPS, which is neighborhood radius, mean samples, minimum points for form a dense cluster. How it works. If your points in low density areas, which labeled as -1 are detected as outliers. When we use DBS-CAN, we don't need to predefine number of clusters. We handle noise and clusters of arbitrary search effectively. So the outcome will be the identifiers rare and abnormal cases will miss by other techniques. So the third one is local outlier factor. So this is to detect local anomalies based on densities. So the method we use is LOF. How it works, if you compare the local density of a point to its neighbors, if points with much lower density are marked as anomalies. So the parameters we use is n neighbor equal to 20 and contamination equal to 5%. Why we use LOF? Because it will capture local data structure, detects suitable context-specific anomalies. The outcome will be it will identify outliers that may be missed by global detection methods. So the next part is 3.0 evaluation and validation of models. So the first one is classification. So the course evaluates a multi-label classification model by calculating metrics like accuracy, Hamming-Loss F1 score, which includes micro, macro, weighted precision, and recall for each target variable. It then calculates the average of each metrics across all target variables to give an overall performance measure of the model. So this is the code for classification. So this is the result of classification. So accuracy indicates the model correctly predicted about 89% of the targets. Hamming-Loss shows a low error rate in multi-label predictions. The F1 score was calculated using micro, macro, and weighted average to capture performance across all classes, considering both common and rare ones. Additionally, predicting and recall will show the model's ability to correctly identify positive prediction and capture all relevant outcomes. So the second one is clustering. So for evaluation and validation of clustering, the evaluation of clustering model will carry out by using various cluster validation metrics to assess the quality of clustering results. The CO score indicates that the cluster is reasonably well defined, as values closer to 1 reflect better cohesion and separation. The Davis-Bode index provides an internal evaluation of cluster compactness and separation, where lower values indicate better clustering. The Kalecki-Harabas index evaluates the variance ratio between and between clusters, with higher values indicating better defined clusters. And the last one is inertia, also known as WCSS, were calculated to assess the compactness of clusters. So the right side is the code and the result of clustering. So the last one is anomaly detection. The evaluation and validation of anomaly detection is performed by using appropriate performance metrics such as accuracy, F1 score, recall, and precision to assess the effectiveness of each technique. The evaluation results were compiled and visualized in a structured format using a pandas data frame. This step is essential because to understand which model performs best in identifying anomalies accurately. Among the models evaluated, isolation forest and DBS-CNN show relatively higher performance across all metrics, especially DBS-CNN achieving the highest accuracy. So the right side is the code and the result for anomaly detection.
Okay, this is the next section is 4.0 data visualization and interpretation. So our classification model performance was visualized using a horizontal bar plot, which compare the different performance metric. The key metric was examined include accuracy, Hamming loss, F1 micro, F1 macro, F1 weighted, precision, and recall. Each of these metrics provide insight into different aspects of our model effectiveness. So here is the breakdown for is a breakdown of the performance metric we use. Accuracy tells us how many instances were correctly classified overall. And Hamming loss measure the fraction of incorrect prediction in multi-label classification. And F1 micro calculate the global F1 score by considering total true positive, false positive, false negative. So this is useful when dealing with imbalanced data set. F1 macro takes the average of the F1 score across all classes, treating them equally. F1 weighted is similar to F1 macro, but adjusts for a class imbalance by weighting each class with one score based on the number of true instances. And precision indicate how many positive predictions were actually correct, which is crucial when false positive need to minimize. And the recall measure how many actual positive were correctly identified, which is important when false negatives must be avoided. Okay. So this is the result of the plot. For accuracy, we achieve an accuracy of 89%, meaning that our model correctly classified 89% of instance. This is a strong performance. And Hamming loss at 11%, our models make incorrect prediction for about 11%, of course, since a lower Hamming loss is better. This suggests a good performance for our models. So for F1 micro, also at 89%, which match our accuracy, this indicates that our model is performing consistently across all classes. And F1 macro, we see a drop to 47%, which suggests poor performance on raw drugs classes. F1 weighted at 86%, this metric account for class imbalance and confirm that while the model performed well overall. And precision micro, we have 89%, meaning that most positive predictions were correct, and our model makes relatively few false positive errors. And the last one, the recall micro, is 89%, showing that our models correctly identify 89% of actual drug users. So move to the next one. We have the plot called prediction accuracy for each drug well horizontal bar chart. First, we compare the true label y-test with the predicted label y-print, and we're generating a Boolean array where 1 represents a correct prediction and 0 represents an incorrect prediction. Then we computed accuracy per drug by dividing the number of correct prediction by the total test samples for each drugs. If in the end we use a bar chart to present the result, then ensuring the chart is clear and easy to interpret. So this is the result of the code, and we get some insight, which is like high accuracy drugs like orchodone, morphine, and hydromorphone have nearly perfect accuracy. This suggests that these drugs have strong distinguishing feature in the dataset, making them easy for the model to classify. And then low accuracy drugs such as cocaine, ethanol, and benzodiazepine show noticeable lowly accuracy. This suggests that the model struggle to differentiate these drugs, possibly because of overlapping feature of bias toward more common drug classes, leading to misclassification. So move to the next one. This is the plot for the clustering problems. Our goal was to identify the geographic cluster of overdose incidents. Here, how we approach. We use the K-mean clustering to group the latitude and longitude data. The algorithm identified the cluster centroid, which represent the mean position of all points in a cluster. We extracted these cluster center and displayed them in a readable format for analysis. So the left side is the result of our clustering. And we can see the overdose incident are partially grouped, and the red X marker represent a cluster centroid on the map. And we successfully identified 3 high-risk locations as first, Marble Shelton CT's 06484, and second, the Crichton Avenue, Bean Hill, Norwich CT 06360, and the third one, 16 Progress Circles, Newington CT 06111. And these locations stand out as a potential hotspot for drug-related incidents. Targeted preventive measure can be implemented in this area to reduce overdose incidents. And move to the third part, which is the anomaly detection parts. To compare the different anomaly detection model, we created a line plot to show how performance change across key metric. We use different color for each models, making it easier to differentiate trends. And we focus on 4 main evaluation metric, which is accuracy, F1 score, recall, and precision. And this is the result of our performance trend across model line plot. So you can see the isolation forest perform consistently well across all metrics, and DBS-CIN suffer a drop in F1 score and recall but recover in precision. And the last one, the LOF, performed the worst with low F1 recall and precision score. So from this, we can conclude that isolation forest is the more reliable model for anomaly detection in our dataset. Move to the next one. I will present our anomaly detection analysis using principal component analysis and different anomaly detection models. Our goal was to reduce the data complexity and visualize anomaly effectively. So we apply PCA to reduce high-dimensional data to 2D while preserving variance. We use scatter plot where blue point represent normal data and red point represent anomaly data. We compare 3 models, which is isolation forest, DBS-CIN, and LOF. So this is the result of the code. And we get some insight. We know that isolation forest and DBS-CIN detect more anomalies, making them effective for irregular pattern and varying densities. LOF more conservative, detecting fewer anomalies, meaning it may miss some outlier. Anomaly was scattered across the dataset, confirming variation in model behavior. So for the best model suggestion, if data have irregular pattern, DBS-CIN and iOS isolation forest are better choice. If data is densely packaged, LOF might be preferable. Next one, I will present our anomaly detection analysis using a Venn diagram to compare anomalies detected by 3 different methods, which is isolation forest, DBS-CIN, and LOF. Each method label anomalies as 1 and normal data as 0. The Venn diagram helps visualize the overlap between these methods, showing which anomalies were detected by 1, 2, or all 3 models. So you can see later you will see the non-overlapping areas, which means the unique anomalies, which detected by 1 method only. And the overlapping regions means the anomalies detected by 2 or more methods. And the center intersection means the anomaly detected by all 3 methods. And this is the result. From the result, we can get some insight, which means isolation forest detected like 452 unique anomalies, making it highly sensitive to outlier. LOF found 551 unique anomalies focused on local anomalies based on the neighbor relationship. DBS-CIN identified only 75 unique anomalies, but it had significant overlap with other methods. And 119 anomalies shared with the isolation forest, 20 anomalies shared with the LOF, and 21 anomalies detected by all 3 methods. So this suggests us that isolation forests capture global anomalies, flagging more points. LOF detect local anomalies, working well for dataset with neighbor structure. DPSCNN identify anomalies with denser outlier region, leading to moderate overlap. For the next one, this is a confusion metric analysis to compare anomaly detection result between different models. So we will compute the confusion metric to compare the isolation forest versus DPSCNN and the isolation forest versus LOF. So the component we have true positive, which means both model detected as anomalies, and true negative, which means the both model agree as normal. For false positive means one model flag as anomaly but the other does not. False negative, one model miss an anomaly detected by the other. And this is the result of the isolation forest versus DPSCNN. And the analysis show the true negative both is 2,270. The true positive is 22, false positive is 15, and false negative is 87. Which means that DPSCNN and isolation forest share some agreement but have difference in anomaly sensitivity. And this is the result of isolation forest versus LOF. And we found out the true negative is 2,176, true positive is 4, false positive is 109, false negative is 105. We can know that LOF detect anomalies very differently from isolation forest, leading to high false positive and unique detection. And move to the last one. After the comparison of the two diagrams, we can get some key observation, which means DPSCNN and isolation forest show better agreement in anomaly detection than LOF. LOF detecting many unique anomalies, meaning it is more sensitive but may have more false alarm. Only 4 anomalies were detected by both isolation forest and LOF, indicating very different detection behavior between the two models. DPSCNN and isolation forest have a higher overlap in true positive, suggesting DPSCNN is more aligned with isolation forest than LOF. So this is a summary for the whole visualization process. For the classification model performance, we can achieve 89% accuracy but have had a macro F1 score of 47%, indicating difficulty in classifying minority drug classes. And high accuracy, like almost 100% for oxycodone and morphine. Moderate accuracy, like 60 to 70% for cocaine and benzodiazepine. And second, we have Kevin clustering insight. We know that we identify like overdose hotspot in Shelton, Norwich, and Newington. Highlight the priority areas for targeted intervention. And anomaly detection comparison, we know that the best performer is isolation forest because it got the highest detection rates. And the balance approves DPSCNN is better. And the weakest performance is the LOF because it missed many anomalies. And the PCS catapult analysis show like isolation forest and DPSCNN detected more anomalies. LOF was more conservative, identifying fewer anomalies. Venn diagram finding, like unique anomaly detected for isolation forest is 452, LOF is 551, DPSCNN is 75. Minimal overlap between the model indicating a different detection strategy. So for the confusion metric, we get some insight like DPSCNN align closely with isolation forest, showing better agreement. LOF flags significantly more false positive, making it less reliable. And the final kick takes away, the model effectively classified the drug cases despite challenge with minority classes. Kevin clustering pinpointed the key overdose hotspot, aiding in strategic intervention. Isolation forest and DPSCNN emerge as the most effective anomaly detection technique, and this insight can help us to enhance the predictive model and guide targeted prevention effort.
Last part is our conclusion. So this is the summary for our report. So in conclusion, so this report will analyze accidental drug-related deaths dataset used by using classification, clustering, and anomaly detection techniques. The key findings in these reports is first, random forest. It is most effective for classifying drug information, especially minority drug classes. So the second one is K-means clustering. It is successfully identified overdose hotspots by geographic location. And the third one is isolation forest and DBS-CAN, which are best at detecting outliers and unusual patterns. So for the implications, our project indicates the model support early warning system and risk assessment tools. It has clustering and anomaly detection aid in resource allocation and targeted interventions. So for our future recommendations, we will recommend that the we should expand dataset with more recent and diverse data. We apply advanced model such as XGBoost and Light GBM. We also can use SMOT to handle class imbalance. So we can enhance prediction with behavioral features also. And last, we can apply careful cross validation and hyperparameter tuning to improve our project. So that's all for us. Thank you.
So this is our Python code used in this group assignment, and the code can all run successfully and completely. Okay, that's it.